Okay, so like I said, these regression models are going to be for Desmos. They're posted where the video is going to be posted. And I'm going to have to kind of click back and forth a lot to use Desmos. But I wanted just to show you, and hopefully you've done line of best fit before, which is just, like I said, linear regression. So for the first part, just for today, I want you to work on finding the line of best fit, which is just linear. So if you look back at these models, we're just going to use this first one. And you're probably used to mx plus b. We're just going to use ax plus b. Same difference. But all of them are going to be linear. On Monday, we'll start talking about using these other models to get an equation based on the data. So you have all this data. You got your x's, you got your y's. First thing you want to do is get this regression model in Desmos. So I'm going to show you how to do that. So I'm going to stop sharing here and start sharing Desmos. Okay, so when you go to desmos.com, pull up the graphing calculator, and you might, I have the data in front of me, so over at the side there's a plus sign. So when you're doing these data regressions, start with that plus sign and choose the table. The table is going to give you this x sub 1 and a y sub 1. So you type in your x's, 10, 20, 30, and it sees my pattern, so I can just keep hitting enter. It went all the way to 90. If it's not a pattern, you'll just have to type them in individually. Like 55, 82, 108, 130, 153, 181, 206, 224, 260. Okay, so, and you don't see anything on your screen because this is only going from 6 and -10 and stuff. So what you want to do up here, there's a little wrench. You click on that wrench. Don't worry about anything else really, just your x-axis. Change this so that it makes sense. So my x numbers are going anywhere from 10 to 90. So I'm going to change this from 0, because I don't want to start right at 10 and have a dot right on the side of the screen. Tab over to 100. So that will get all of my x's in there. And it looks like my y's, the lowest is 55. So I can start with 50. And the highest, 260, so 300. And it doesn't have to be perfect. Now click on the wrench. Now you can see that data. And yeah, of course, you know, that is a very nice linear set of data. Not perfect, but definitely linear. No question about it. You can zoom out a little bit if you want to see better. Click and move it around. Okay, so this is where you need the model. And that model that I was showing you was y1, y sub 1. But all you have to do on your keyboard, I'll even show it to you here. All you have to do is the y and the number 1, and it will do the little subscript for you. You don't have to worry about making it do that. But then you don't do equals, you do the little, I think it's called a tilde. I don't know if the English people. I don't know if that's down here on your functions anywhere. I don't see it on the keyboard on the Desmos. So what you have to do is it's shift, and it's right there beside the number 1. There's a key that should have that little tilde mark in it. So now I'm going to do A times x sub 1, so you can just do x1 again, plus b. Get rid of this keyboard. And this shows you all the stuff you need to know. So here's your equation, 2.48. So I'm just going to round that up to y equals 2.5 x plus, looks like about 31.03 if you do, excuse me. And also, these R values, that R squared, if you've done that before, that is your correlation coefficient. This R, which is 0.999, and that's important too. So, I'll show you on. Go back to, okay, so I've done all the calculator work now, so answering the questions, make sure that, so you'd say the regression model we got was y equals, it was about 2.5 x plus, it was 31.03, so close to 31, we'll just leave it that way. All right, so now this is what's called the prediction model. Prediction. It is your line of best fit or regression model. But this is what you could use to predict what's happening anywhere. This is the actual data. This is actual. So you need to know for this unit, the word interpolation means when you predict for X values that are within your data, so any number from 10 to 90 would be an interpolation. 54 is in the data. So 54 is probably going to give us some number in between 153 and 181. If this is a good prediction model and this is nice and linear. And all you're doing is plugging it in. So what is y 2.5 times 54 plus 31? I'll change to black in case I go over into the blue part of the screen. So grab your calculator. I say that and mine's not handy. Grab your calculator. 2.5, you'll already be on Desmos, so you can plug it into Desmos. 54 plus 31, you get 166. 166. So what's the prediction for x equals 54? 166. And like I said, it does come in between those numbers. The word extrapolation means that you're actually going outside of your data. And this could be dangerous because just because it's linear inside your data. Now we know nothing about what X and Y stand for, so we can assume that it's just going to keep on continuing being linear, but there are some word problem cases where extrapolating is dangerous because you don't really know what's going on beyond the data. We'll see one like that. But for this, you still just plug it into your prediction model. Just know that when your number 120 is well beyond 90, so that's extrapolation. Plus 31, 2.5, 120 plus 31 gives me 331. All right, residual. This A stands for actual, the P stands for prediction. So a residual is how close is your line of best fit to the actual data. And I can only ask you for a residual when you have actual data. I can't ask you for a residual for 65 because you don't know the actual 65. So the actual answer is 206, so it's the actual, minus, well, you're going to have to figure out what's the prediction, 2.5 times 70 plus 31. 2.5 times 70 plus 31. The actual is 206 also. So we get a residual of 0. And that's good. That means that a lot of this data has fallen right on the line. If your residual is positive, if you get a positive residual, that means your actual point is above the line somewhere. And if you get a residual of negative, that means your actual point is below that line somewhere. And then the last one, correlation coefficient. What is the correlation of this data? Well, the coefficient was 0.999, which means that this has the closer this is to 1, and you can't get much closer to 1 than 0.99, the better the model is. So we can say this has a strong, so anything in the upper 90s is strong. And we can see from the data, or we can see from the positive 0.99, it is a positive line that has a strong positive correlation. That's it. But it's getting the data in and getting this prediction equation that makes everything else work. All right. We'd have to edit these long pauses out of the video. Play music or something. I think it's only when I write on it that it becomes long. Okay. So this time, this table, we actually have what the table represents. So it's the fat grams. And just because you've collected data doesn't mean you can't get data points that for two different ones, right? So this is just some data somebody collected. And this is the calories that each one of them has. So is there a correlation between the grams of fat that's in a fried chicken compared to the calories that's in the fried chicken? So we're going to do a regression model. So in back to Desmos, I can just X out the old ones, start a new table, and this time they are not in any kind of order, so you'd have to type them all in. 34, 28 again, 41, 42, 25, 38. And it's important that each one of your X's has a Y value. 410, 320, 500. So if you skip one, you're going to get an error when you try to make the model. 440. Okay, and again, come over to the wrench. They go anywhere from, looks like 28's the low. So I'm going to go from, say, 25 all the way up to, looks like the highest X is 41, so let's just do 50. Yeah, it doesn't matter. You're just trying to get all your data in there. So your Y values go anywhere from 275 looks like the lowest, so 250 up to 500 was the highest, 510, so 550. You can close that. And this way you're just seeing the data, right? You can still zoom out or whatever you want. There's all of your data. So yeah, it looks linear too. Maybe not as clean as the last one, but definitely that looks like there is a correlation there. And the more straight line your points make, the more of a, like this is going to be probably another strong correlation. So in the second one, remember Y1, squiggly, tilde, approximately, that's the approximate sign also in math, A times X1 plus B. Like I said, for today's, it's always going to be the linear model. And there's our equation. Write that down. Y equals, you see down here, your A and your B, or your M and your B, 13.87. X plus, minus 73.35. And pay attention to your R is this time 0.9956. So go to your worksheet. All right. So once you have your equation, y equals 13.87x minus 73.35. And do a couple decimal places if necessary. If it's really close to a number, you can round it to that number. But if it's getting a little bit further away, go ahead and use your decimals. And again, interpolation would be any number that's within that range. So you do 13.8732 minus 73.35. I think you guys can plug that in the calculator. Not a big deal. You get that answer. Extrapolation just means this 52 is higher than or lower. We could have done 12 there, and that'd still be extrapolation. 13.87 times 52 minus 73.35. And again, the calculations isn't. So what's the residual for 41? Remember, residual is the actual, so find 41. If there were two, I'm not going to do this to you. There are two 28s. I'm not going to ask you for the residual for 28, right? So what's your residual for 41? The actual is 500 minus, and then you're going to have to get the 13.87 times 41 minus 73.35. We'll go ahead and get that number. 13.87 times 41 minus 73.35. That's 495. 495.32. 500 minus that number is 4.68. So the residual is just how far from the prediction is the actual, right? So the actual data, since it's a positive residual, would be above that line. What's the correlation coefficient? What did we say it was? 9956. So not as strong as the last one that was 0.999, but still obviously very strong. So this is strong positive correlation. If it was a negative, it would be a negative correlation. All right, so while that's changing, let me show you on here. Back to Desmos. Oh, it's showing you the line. That's your lineup. So is that your 41? No, here's your 41, right? Up here is that data for 41. And you can see that it's above the line. So like if I gave you that point of data, if I asked you for the residual for 38, you'd get a negative residual because it's below, right? This one is a positive residual, it's above. All right, so let's look at, where are we, the next one. All right, so with these years, be careful about this information. So this is a town in Pennsylvania. Over the past few years, their population. So in 2010, the population was 126,000. In 2012, 120, 857, 20, so forth. But it says use x equals 0 for 2010. So instead of doing the actual year, we're going to say this data started at the beginning. So 0 is our beginning number. Well, 2012 is 2 years later, or if you subtract those two, 2012 minus, that's a 2. The 2014 is 4. 2016 is 6 years later. 8 years later, and 2020 would be 10 years later. So always base it off of the first. And if you're not sure, you can subtract them. 2020 minus 2010, 10. All right, so we're going to plug that data into Desmos. And what that does is keeps you from getting huge numbers in your regression model. Get rid of the old ones, get a new table. Actually, probably could have kept the prediction model. What is it? Y1 A times X1. It will not work if you don't put those little subscripts. So if you're not getting any kind of answer here, it's because it might be you're not using the subscripts and it can't be an equal sign. So if I leave that, so it was 0, 10, 20, 30, 40, 50, wait, 10, oh no, not 20. It was 10, 2, 4, can't type, 6, 8, 10. Get rid of that one. All right, so 1, 2, 6, 120, 8, 5, 7. And see, it's starting to go ahead and do the model as I go. So if that's already, if you don't clear that out every time, it'll fix it for you. 110, 693, 105, 743, and 101, 232. All right. So finish the data before you grab the prediction model, which says y equals negative 249 8x plus 126,000. So show you what I'm doing. Because the numbers are so big, the decimals aren't going to have as much effect on them. So I would just do y equals negative 249 8x plus, and then that 125,966 is really close to 125,600. So not going to be perfect. And that's why if there's questions on what is the prediction model, it's going to be multiple choice. Because it's not an exact science. Oh, so my wrench needs to go anywhere from 0 to 12. Then my Y's, looks like the population, the lowest it went is 100,000. And the highest, 126, I'll do 130. There you go. So as you see, my prediction is just a little off of the red one is the one the computer generated. Mine is just a little off of that because I'm down a few. But okay, and the R value for that one is a negative 9.996. So I'm not going to fill in everything. I'm going to go ahead and stay here and do the next one for you. But you could fill in, right? You could plug into that. You have a negative, so this has a strong negative correlation. The residual that it asks for is for 19. When does it? Oh, sorry, for 2018, which is probably going to be 8. Yeah, it's going to be 8. So that residual going to be really close, might be a little bit positive based on my prediction equation, so forth. Okay, so I'm going to clear out this one, clear out this one. I'm going to leave that one. So I'm going to add, can I do it here in it work table? Oh, no, now it's X2. So clear out the whole thing. Yeah, if your table ends up with X2 and Y2, then you'd have to do your equation with X2 and Y2. But the last one, I won't go back, but it's talking about the CD sales, compact disc sales from 1984. And it says use 1984 as 0. So I'll show you this at the end, but it would be 0. The next one was 85, so that'd be 1 year later. 86, 87, 88, 89, 90, 91, 92. So those go right in order. And then your sales were 10 CDs for this record store, and then the next year they sold 253, 607, 1156, 1494, 2010, 2897, 3450, 4104, Y1 tilde A times X1 plus B. So when you look at this data, so those, the X's are fine, but now I need my Y's to go somewhere from 0 to 5,000, it looks like. There you go. And you can see that information. And again, not bad linear. If the points were everywhere, you'd see like this has 0.989. So it's got a pretty good, still a strong correlation. You can write your equation in. So 523.35 and negative. So that this last one is pretty well off in that 0 year when they sold 10. Of course, they couldn't sell negative, so that wouldn't make sense anyhow. But if you look back, so here's the actual problem. This is what I was saying with when you start getting into extrapolation for this one, you know, what is going to happen when you get up to 2020? Do you think the CD sales are going to be way up there? Like the prediction would have them well up there when we know CD sales aren't that great anymore because nobody buys CDs anymore, right? You got all other kinds. And that's like if you looked at cassette tape sales back in the 70s and 80s and how much they would be, and now none, right? So extrapolating doesn't always work. Some things change. Interpolation makes sense because it's within the data. And even, yeah. All right, so I'm going to stop right there with